Hello class, this is CSE-5250, Section 60, Week 3, Fall 2023. If you look onto Canvas, you'll notice that there are two PowerPoint slides for OpenMP. But before we get to that, I'd like to show you an analogy for processes versus threads. This is a blog post by Brian Mbieli. A process, this is a 3-minute read, but I'll just summarize it for you. A process is like a restaurant, full of workers inside. The workers are like threads. When the employees clock in, that's like the program being loaded into memory. The individual employees working on different things, say one's on the grill, one's operating the fryers, one's operating the cash register, another is, say, cleaning the toilets. Each person is like a thread. They are operating something, they're doing something within the restaurant, but there are so many things to do in the restaurant that no one person can ever try to do it all at once. Hence why there are multiple employees, multiple threads working on those things. So if a process is like a restaurant, the people inside, the employees inside, are the threads. Another instance of the same restaurant is another process. So that's basically a quick read for you to contemplate on. I'd like to get started on OpenMP. There are a few programs for you to follow along with. So let's begin. So OpenMP is an API for writing shared memory parallel programs. The way OpenMP works is that you have directives that you write that will make certain parallel blocks in your code. What happens is the compiler and the runtime system determine the behavior of threads. So it's easy on the programmer to make parallel programs. We say that this is being done at a high level compared to, say, low level. We're going to look at pthreads later on, but basically what OpenMP lets us do is easier compared to, say, pthreads. OpenMP was developed by programmers who believed that writing large-scale, high-performance programs using API was too difficult. So, as I said, OpenMP allows for parallel programs to be made at a higher level. Oh, and the MP stands for multiprocessing. So OpenMP is an API for making multi-threaded parallel programs. In our restaurant analogy, it's like you just hired more workers to work in the same restaurant. So what we can do to get started is to write a parallel program like this. What I'm going to do is the same thing. So let's just get started with writing the whole thing out together. So include standard.io.h, include standardlib.h, and that might be a good idea for me to zoom in here. So hopefully 200% is a good zoom level. And the third thing we need to include is omp.h. Because OpenMP has a library that has specific functions that we need to use for this Hello World program. I'm gonna write in a function prototype that has the function, a function prototype for a function that says hello. Hello world. Hello. It's a void function with an input of, with a argument of void. Now we can write the main function. This is a little bit, this may be a bit different from what you've seen, or maybe this is something you're familiar with, but either way, we're writing a program that takes in command line arguments. So, int argc character star argv square brackets. Get number of threads from command line, so we're gonna do that. Int thread count equals str toll, and then we have 3 arguments. argv1, because argv0 would be the name of the program itself. We don't need to worry about the second argument, so I'll just pass in null. And the third argument is we are parsing something that was entered through the command line as a base 10 value, so 10. And here's the first OpenMP related thing I'm gonna write. Now the keyword pragma is something the keyword pragma is something that is available to C and C++, but if you have pragma OMP, then that means we have something that's specific to OpenMP. I'm gonna then write parallel, which tells the compiler, hey, this is going to be a parallel section of code. We're gonna, at this point, if the program was single-threaded, it's going to fork into multiple threads. And then those multiple threads are gonna do something. But I'm gonna keep going and add in this clause here. Num threads, and we set that to thread count. So let me just put the cursor back there and type that in. New line, and then we type in hello. So what is going on here is, as I just said, up to this point, the program was single-threaded. In fact, the program started out as a single-threaded program, a single-threaded process. It's going to reach this point. It's going to fork into multiple threads, however many based on what we entered during the command line. And each thread is then going to call the hello function. And then once that's done, they're all going to merge back with the main thread. That should be when we exit this parallel block of code. Alright, that's the main function. So now we have to write our hello function. So void hello. And then we type in, what we're going to do is write a hello world program that prints to the screen its thread ID out of how many threads there are. So we need 2 variables for that, and we need 2 special functions for that. Int my rank equals OMP underscore get underscore thread underscore num, left and right parentheses. This is a function that will get the thread's thread ID or thread number. Int thread count equals, it's going to be a similarly named function, but it's OMP get num threads. And here, I should mention that this program is actually a C program. I opted for writing it in C++ because I opted to write it in C++ to show what would happen if you did so. I will say right now, it will work as a C++ program. It says that there are some features in C++ that might break if we were to use OpenMP. I'll show you one in a little bit. So we have to print this out using printf, because if we were to use cout, weird things might happen. But first let's write it the right way. I guess write it the way that wouldn't break. And that is with printf, we're gonna write in hello world from %d of %d. I'm gonna end it with an exclamation point, and then \n to indicate new line. And then we need to have the values for these %ds, and those are going to be my rank and thread count. And that's it. Now, if you are using Visual Studio, there are a few extra instructions you need to do. I'm going to advise you to use Visual Studio 2019 because Visual Studio 2022 might make this process a little bit trickier. I know this from trying it myself. But if you know a way of making it work, definitely let me know. Here's what we do. If you are using Visual Studio 2019, go to Build. Actually, no. Go to Debug. Go to Project Properties. Project Debug Properties. It's the very last option down here. Click that. A pop-up window will open here. Go to the setting that says C/C++. Open this menu. Go to Language, and you'll see a setting for OpenMP support. If this is a new project, it will definitely be set to off. You want that to be set to on, and then click OK. And that's it. Now you can run the program, right? Not quite. You see, if this is a program that takes in command line arguments. If I just click local Windows debugger, it crashes. That's because it's expecting command line arguments when I gave it none. So I'm going to abort that. Here's what I'm going to do instead. Build solution, or it's Control-Shift-B. I'm going to move my webcam because I need to show this exact operation. Click in the Solution Explorer, click the solution itself. It should say solution name, and then something of something project. Right click that itself. Open folder. Right click that. Open folder in File Explorer. Now these instructions are specific to Windows. Depending on whether your project is an x86 or x64, you might need to go down into an x64 folder before you reach this debug folder. But if you do, once you find the debug folder, you will find the compiled executable. We're not done yet, however. What you then need to do is click the address bar itself. Type in PowerShell. Press enter, and then now we have PowerShell. This is a Linux-like command line interface for Windows. what we do now, since we built the program already, the program's ready to go. So what I'm going to do is type in // and then the name of the program. This is a project file from last semester, so that's why the name is different. So CSE-5250 _ SPR 2023 _ open mp _ test.exe, because this is an executable file. And it still crashed. And that is because I did not write any command line arguments. So I need to do that. Let's do 4. There we go. If this works, you should see hello world from such and such thread out of such and such quantity of threads. So hello world from 0 of 4, 1 of 4, 2 of 4, and 3 of 4. If you were to run this multiple times, there's a good chance that you might get the threads out of order. And that is to be expected. That's because the threads are fighting for the same resource. We are technically having a race condition here. So let's go back to the PowerPoint presentation. If you are compiling this on a Linux system and you want to compile the program, this is the command that we use. gcc-g-wall-f-openmp-o, and then the name of the file for the final executable, and the name of the source file here. As I said, when you run the program, you will get hello from thread something of 4. But the order may be random. I've included the instructions on how to turn on OpenMP support for a Visual Studio project. Don't confuse this for Visual Studio Code. Visual Studio Code is a whole different program altogether. I will say right now that Visual Studio itself is a hefty program. Depending on what plugins you install, it might be at least 1 gigabyte in size. So yeah, as I said, the program runs as a single-threaded program up until we reach this pragma line here. That's when the program forks into multiple threads, and then each thread calls the hello function. Each instance of the hello function being called is being done on a separate thread. Each thread has its own ID, and that's how we have each thread having a similar but different hello world message. So this section here is just a breakdown of what the program is doing. There are a few OpenMP terms. When a program forks into multiple threads, that resulting group of threads is called a team. Usually, it's a thread with ID 0, the master or the main thread, that is the parent of that entire group of child threads. So, basically, the program starts with thread with ID 0, the master or main thread. It forks and produces a bunch of child threads that constitutes an entire team. When those threads finish executing, they wait at the end at a barrier. All of the child threads then terminate and then join back with the parent thread. At the end of our execution of a parallel block, our threads hit a barrier. Threads wait at the barrier, and then once all the threads are there, the child threads terminate. And then the parent thread continues executing the next block of code after that. This is called the fork and join model. So a process forks into multiple threads. All the threads eventually join back with the main thread. This is just a quick slide on error checking. As you can see, we did encounter an error, and that's when we had our program crash because we gave it no command line arguments. It might be a good idea to set a default value here, so even if you have it so that you forget to do that, the program will still run just fine. Just something to keep in mind. Okay, where are we at? 21 minutes. Okay, so that is the first program, and it is a Hello World program. The second program is a program that I encourage you to try for yourselves. Try rewriting it for yourselves. I have the source code on Canvas already, so what you could do is just go there, copy paste all the code. What I'm going to do is undo all of this because I had already written it previously. So there we are. Let's look at the next PowerPoint slide. This is going to be Chapter 5B. It's part 2 of Chapter 5. We're gonna look into making a program that implements the trapezoidal rule. If you remember from calculus, the trapezoidal rule is a way of estimating the area, approximating the area under a curve for which we have a function f of x that is defined, and new gremlins from Build-A-Bear Workshop. Anyway, let me just there we are. So now we have a space to draw on. So say we have a function f of x. It looks like this. And what the area under the curve. In calculus, what we can do is divide the whole curve into a series of strips. And the areas of these strips can be approximated as either rectangles or trapezoids. When we take the area of a trapezoid, what we need to do is, if we have a trapezoid here, it's going to have 3 lengths that we care about. The length and 2 different heights, h1, h2. We add the 2 heights together, we add the 2 heights together, h1, h2, multiply that by L, and then we divide the whole thing by 2. What's going on is we're taking another copy of this trapezoid, rotating it around so that we get a rectangle, or I guess in general a parallelogram, and then we're taking the area of the entire parallelogram and dividing it by 2 because we had to duplicate the trapezoid. So This is f of x. We have our start points A and B. The one thing we need to enforce about this is the width of every strip, the width of every trapezoid is the same. We call it delta x. So all we need to do is to find the two heights for each trapezoid. That is defined by f of x. So what we need to do here is find the value of this point, this point, this point, this point, and so on until we reach this point. So here's how it looks like. The area for one trapezoid is going to be f of a plus I delta x. Plus f of a plus I plus 1 delta x. And then times delta x, all divided by 2. And that's the area of one trapezoid. We have adapted this trapezoid area formula into this form here, where if we know the 2 points along this interval here, we have a plus some number of delta x's after that. So if we started at, oh, and this I is not the imaginary unit I, it's just a number, a real number. Because sometimes summations here use a start value of I, sometimes I'll use k. Just keep in mind that it's going to be typically either that or I or n. For our purposes, we're using I. So we start at A and we move sideways some number of delta x's. We find f of that value and we get the first height. And then we move one more delta x after that. So we get the next height. We add the two heights. These should be in parentheses. We add the two heights, multiply it by the width of the trapezoid, and every trapezoid width is the same, delta x. We divide all of that by 2. So all you gotta do is add. All we have to do is add all those trapezoids together. Here's the thing though. When we do this, we're gonna have, say, when we do this, we're gonna realize that every term is being multiplied by delta x over 2. So what we can do is just rewrite the whole thing. So it's delta x over 2 on the outside of the summation. So all we're doing is adding all of this together. F of a plus I delta x plus f of a plus I plus 1 delta x But here's what I'm gonna do. I am not gonna move the divide by 2 on the other side. So that way, when we expand the summation out, that way when I expand the summation out, let me just erase this, all of this. When I expand out the summation, which is a thing we can do, what we're going to have is this. And I'm just going to simplify it here. So we're going to have a big summation. So it's f of a over 2 plus f of... I'm just going to call this thing a1, a2, a3, and so on. Probably not the right terms to use, but just follow with me here. So I'm going to call this A1. So this represents the addition of the two heights in our trapezoid sum. But the thing is, we're going to see this again. So this is the first trapezoid. Plus f of A2 over 2 plus f, oh, this should be an 1, a2 over 2, this is trapezoid 2. And this goes on until we get to the last trapezoid. So if we have, say, if we have n trapezoids here, it's f of a, and then f of a of 1, f of a1, f of a1, and f of a2. So if we have n trapezoids, eventually we'll reach the last trapezoid, and that is going to be f of a n over 2 plus f of b over 2, because we will have reached the final point on our interval, and that is point B. So what happens here is we have a bunch of f of ai divided by 2, but there are 2 of them. So we can just add them together, so instead we're simplifying our sum here. So what we're doing is a summation that looks like this. F of ai in parentheses plus f of a plus f of b all over 2. But then all of this is also being multiplied by our delta x. Which is why, if you're to look at the code for this program, you'll see the starting sum be f of a plus f of b all divided by 2. And then it's going to be f of a plus some number of delta x's after that being added into a sum. And then we're going to multiply the sum by delta x. So I'm going to pause the recording here, and I'm going to start setting up I'm going to pause the recording here so I can set up Visual Studio so I can look into what is going on with the program. Alright, so here we have the entire program already coded for us. But let's look at each line of code to see if we can make sense of what we have. Okay, here we have our function prototypes. We have our main function. We need... Okay, so these variables are slightly different from the variable names I used in here. But here we have a variable to store our result. We need to have two other variables for our left and right endpoints. We need an n to represent the number of trapezoids we are using to get our area. And then we have a thread count, which we have our strtool function again. One thing that the book says to do is to use the scanf function. If I did that, the program might say something. Here we are. Scanf may be unsafe, so we need to use scanfs instead. But it will do the same thing. This program is copied directly from the book. It's just I had to adapt it to account for these kinds of changes. Here's a parallel section again. So, as was before, we have our parallel section forking into multiple threads. It forks into multiple threads. Each thread then calls the trap function. It's going to get A, B, N, and the address of the global result. So each thread's going to call this, and then it's going to tell us the area of our final trapezoid. So if I build this and run it using this, because this is the same program as the Hello World program as before, I'm actually able to use the same PowerShell. What I would recommend you do is I would highly recommend that you have separate projects for your OpenMP projects. So, when we run this, I'm gonna run it with, say, 4 threads. Don't do the same mistake that I did initially by adding the commas when I type in the values. That's gonna screw everything up. So don't do that. Only use spaces as separators. So I'm gonna try 1,000 trapezoids. When I do that, I get an area of our trapezoids to be 333.3335. If you are to run this through a calculator, and I first actually need to explain what f of x is. I defined f of x as being x squared. So if you were to run this through an integral calculator, or if you take the time to do the math using the power rule, you will find that that is basically not too far off from the actual value, which is 333 1/3. So 333.333 repeating. So it works. So what's going on in this function? Well, here's the thing. You remember the scope of a variable? You can think of it as the region within curly brackets in which a variable is in. So all of these variables here have their scope is the area within the curly brackets here. But if we have variables outside, if you have variables outside any function, they're outside any groupings of curly brackets, then what we have is a global variable. But more specifically, we have what's known as file-wide scope versus function-wide scope. So these variables here, they're function-wide scope because they are enclosed within a set of curly brackets. Same for these variables here. If if we had a variable that was outside any groups of curly brackets, then that is file-wide scope. Those are global variables. Threads have a few variables that might or might not be shared between multiple threads. When this function is called, it will be called by multiple threads, and each thread will have their own local variables. That is private scope. Sometimes you'll have threads having variables that are shared between other threads. In our case, that would be global result P. That is, actually this is a pointer to our global result, but the value at that pointer is something that is shared between all of the threads. So that is shared scope. So when this program runs and the program forks into multiple threads, each thread is going to have these variables. It uses h to denote the width of the trapezoids, whereas I used h to denote the height of the trapezoids. So that's just one thing to keep in mind. I used variables slightly differently from what the book uses, but the code still works regardless. So keeping in mind that h, that's my alarm. Keeping in mind that h is our width of the trapezoids rather than the heights of our triangles, we are going to assign that value b minus a all over n, and that is going to give us the width of our trapezoid along the entire interval from a to b. It's going to calculate a local n, which is going to be the number of trapezoids divided by the thread count. It's going to calculate a local a and a local b. A is the leftmost endpoint, and if we add the thread's rank and its local n and multiply that by h, that's going to create a new value. Okay, so how this for loop works is it's going to start off by, if you look back at this example, if you can imagine the work of adding all these trapezoids being divided between two threads, what's going to happen is one thread is going to have, if you imagine the work being equally divided as well, one thread is going to work on these trapezoids, and another thread is going to work on these trapezoids. But they must start at different locations, otherwise bad things will happen and you'll add the same values redundantly. So, one thread must start here, another thread must start here. And these threads are working on contiguous blocks, so one after the other until they reach the end, which is right next to the beginning of another thread's work. So we have to divide the work evenly into concurrent blocks. So that is what this local A is. It's that thread's starting point. Local B is that thread's end point. So the interval AB is itself divided into smaller intervals. Each thread gets an interval, but each thread has some number of trapezoids along those smaller intervals. And each thread should have roughly the same number of trapezoids amongst them. So this summation here, we can do this using a for loop. This here, we can just calculate that after the fact, and then we can just multiply everything by delta x at the end. That's kind of what's happening here. First, we calculate f of local A and local B. That is the same as this portion here, but instead of this being the whole interval, it's a portion of that whole interval. Then we just add f of x one after another, where the x is local A plus some number of delta x's. So x equals local A plus I times h. We increment my result by that f of x. So if x is local A plus some number of I times h's after that, we can use f of x. We can use our function here to calculate f of x. Increment my result by that, and then once we have the whole result, we multiply it by h. We're not done yet. We have only the sum of a portion of all the rectangles. Of all the trapezoids, I mean. We need to have the threads communicate with one another, we need to have all the threads. Okay, so each thread was doing the work of calculating and adding the areas of individual trapezoids. No one thread is going to have a situation where the result of the next trapezoid's area is dependent on the last one. So we say that communication on that part, the calculation of trapezoid areas, it doesn't need any communication between the threads. However, we need communication between the threads when it comes time to add all of the areas together into one final global result. So here is what we call a critical section. When all of the threads have finished this part here, we enter a critical section that says, hey, one thread at a time. This is because if more than one thread were to access this line of code at the same time, you might have a situation where it may be the case that you have the wrong value at the end because two values are trying to add the same thing at once. So we enforce mutual exclusion by turning this into a critical section using pragma OMP critical. Now we have our critical section. One thread at a time, but once each thread has added its result to the global result, one at a time, we will have our final result, which is 333.333. Right? There is another way of writing the same program here. We could instead have our trap function return its portion of the area. We can have the trap function return the sum of that thread's trapezoids. So, double, and instead of having a global result being passed in as an argument, we have 3 arguments now. Double trap and no more address. We're gonna have to make a few changes here. Among them is removing the critical section and instead return my result. We need to change our parallel. We need to change our parallel section though. It would look like this. And keep in mind, I do have the PowerPoint settings that explains all of this as well. So instead, so here, trap is now going to return something, but we need to store that something in a global variable. Here's how. If you have a if you have a code block followed by an OMP parallel section, what you can also do is enclose the whole thing in curly brackets in case the whole thing extends beyond just one line of code. So, curly brackets, I'm going to add in pragma OMP critical. So our new critical section is here. Then we add in global result plus equals trap. So what's happening now is this. The program, as a single thread process, hits this parallel section here. The program forks. Each program calls trap one at a time, and then adds its result to global result. I said one at a time because this trap function, this whole thing, is a critical section. We ended up accidentally turning our multi-threaded program into a single-threaded program. So it turns out that is not what we want. So here's what we're going to do instead. I am going to define a view variables right outside the critical section. So here's what's happening now. I split the whole thing into two pieces, and one of them is the critical section. So now when every thread executes this parallel section, they're gonna be calling the trap function all at the same time now. The only thing that can't happen at the same time is incrementing global result by my result. So now we've solved the issue of accidentally turning our parallel program into a serial program. OpenMP has a way of writing this in a simpler way. But before I get to that, you want to see it run? Of course you do. Alright, I'm going to Control-Shift-B to build the whole program. I have PowerShell here already open, so I can just clear, clear, clear. Call the program again with 4 threads. I'm going to enter 0, 10, 10, 1000. And now we got our same area as before, so it still works. So here's the shorthand that OpenMP introduces. This is based on something that's known as reduction. Reduction is this. You have something called a reduction operator and a reduction variable. A reduction operator is some associative binary operation, and a reduction is a computation that repeatedly applies the same reduction operator to a sequence of operands to get a single result. So, incrementing sum by the values of some array A, each one element of a time. This is a reduction operation of addition, and sum here is our reduction variable. So sum plus equals some value in the array, that is reduction. OpenMP has a shorthand for doing this section of code. All we gotta do is this. We can declare a reduction operator as follows. Reduction. First, we add in the operation, and that is the plus operation, and then we add in a colon, and after that we type in our reduction variable. So now all we gotta do is remove all this code, because we don't need a critical section anymore. It's rather, all of this is going to be equivalent to what we just had previously, where we had a separate critical section in OMP parallel num threads. So global result plus equals trap A, B, N. So this is equivalent to the previous code where we had a critical section in our parallel section. What we did was apply reduction. We declared a reduction operation and a reduction variable. So now we have 2 or maybe 3 lines of code to do the same thing as we had previously, spread over multiple lines of code. So here is what it looks like in the PowerPoint slide. This commented out code is the same as this code here. If you have a Pragma line that is way too long and need to separate it between multiple lines, at the end, put a backslash, and then you can just continue on the next line. So the syntax for what's called a reduction clause is as follows. First, it's the keyword reduction, and then in parentheses you have the operator, colon, and then your reduction variables after that. There are quite a few reduction operations you can use for this. Addition, subtraction, multiplication, bitwise operations of AND, OR, and XOR, and then logical operations of AND and OR. And they must be binary operations. They can't be unary operations. So for example, we don't see NOT. There is one weird thing that can happen specifically with floating point variables. It turns out that floating point arithmetic is not associative, so you might have, for example, A plus B plus C and A plus B plus C having different results. More to the point, if your reduction variable is a floating point value, your result might be different based on the number of threads you use. So that's one thing to keep in mind. So yeah, these are the programs. This is the program that I want you to play around with for yourself. What I would encourage you to do is run the program again with different amounts of threads and trapezoids, and see if you can time the program to get different execution times. There is one other thing. Whoops, not like that. We need to assume that there are more trapezoids than threads, so that way we can divide the work by assigning contiguous blocks of trapezoids to each thread. So you can look through the PowerPoint presentation itself. It's basically everything I've just said. There's a process to parallelizing a program that I didn't get to, but here are the 4 steps. Partition the problem solution into tasks, identify communication channels between tasks, aggregate tasks into composite tasks, and map composite tasks to cores. With our OpenMP trapezoid rule, we identified the jobs of computing the areas of trapezoids and then adding the areas of trapezoids. Computing the areas of trapezoids does not require any communication between threads because there is no way that the result of the area of a trapezoid is dependent on the previous trapezoid. The total sum of all the trapezoids will require communication. And then once again, we assume that there are more trapezoids than threads, so we can just divide the work by assigning contiguous blocks of trapezoids to each thread. Alright, that's going to be it for CSE-5250, but before I end the video, there is one thing I want to show you, and it's what happens if we use cout for... What happens when we use cout instead of printf? So let me just modify the code once again. Alright, so I've quickly rewrote the hello world program using cout instead of printf. I've rebuilt the program, cleared this, and here we get multiple threads trying to say the same thing at once. So, what happened here? Hello world from thread, hello world from thread 1 of 4, 0 of 4. So, here's what happened. One thread was in the middle of saying its hello world message when another thread started to say its hello world message in the middle of another thread's message. So now we have threads competing for the same resource of printing this thing to the screen, and we got another race condition. This is worse than the situation where we have threads finishing their work out of order. It only gets worse if we have more threads. You want to see that? Yeah, so if I run this program again, it would say 64 threads. It's not so bad until we realize that hello world from thread, hello world from thread, hello world from thread, hello world from thread 31 of 64, 46 of 64, 27 of 64, 47 of 64. See, it's kind of a mess. So this is why we are using printf over cout. I guess another test thing we can do before I end the video is how many threads can my computer handle? So I did this experiment with my laptop and I concluded if I did this, it would be 8,192 threads. Okay, so at some point the value will be so big that the whole thing just defaults to just one thread. If I instead say 8192, will it work still? No. 4096? No. 2048? I did that wrong. Okay. So my main computer has a limit of 1024 threads. So if I am to run a multi-threaded program on this computer, it will be limited to 1024 threads because anything beyond that, and it'll default to just one thread. So yeah, there is a limit, but it's based on what hardware you have. Oh, hello world, hello world, hello world. Alright. Well, that's gonna be it for this week. Once again, I encourage you to experiment with the program, see if you can get some execution times for yourself using the trapezoid rule program that I gave you. There are ways to do that, including writing in a timer into the program itself. There may be Linux commands that'll help you get execution times, but see if you can get execution times for different combinations of trapezoid counts and different numbers for your thread count. Alright, that's gonna be it. See you next week.